Angelica Rota. She is a PhD student at Polytechnic University of Bari and in collaboration with AGC. So I think you have a split position in Bari and AGC. Working on design for disassembly. It's also looking into the reuse potential of IGUs. You already started that work in your master and now continue in the PhD. So,
yeah.
Angelica.
Thanks, Christian, for the presentation, and good morning, everyone. Then today I'm going to speak you about the environmental assessment that I've done for the reuse process of the post-consumer glass. And starting by the outline of this presentation, I'm going to give you an introduction about the current status of remanufacturing and reuse of post-consumer glass in Europe, followed by a brief explanation of the LCA methodology that I've used. Then I'm going to explain you the scope and the system boundaries that I've used in my study, as well as the assumption of the assessment. And I'm going to then show you the results and the comparison studies that I've done. So the first question that I would like to address is, what is the current status of reuse and remanufacturing of post-consumer glass in Europe? And you might have known a bit about it in the previous presentation, but there's still a lot to say and there's still a lot to work on. So post-consumer glass, first of all, is the glass that has been used in a facade and which it reached its end of life, and therefore it needs to be collected. And this is how a collection of glazing looks like when it's done carefully. Usually, post-consumer glass ends up like this, so crushed and mixed with other construction and demolition waste. But if we want to aim at reusing or remanufacturing the glass panel that we take out of the facade, then this is not possible. This is not the way to do it, because once the glass is crushed, then there is no room for reuse and remanufacturing. And the reuse at the moment is not happening in Europe, or at least some few pilot projects or case studies are happening, but there is no full-scale framework for reuse and remanufacturing. And you might wonder why, and there are many reasons. And as you can see in this scheme, the reason can be classified into different categories. And what I've classified them are in the technical, environmental, economic, legislation, cultural, and logistic barriers. And in this presentation, I'm going to talk about the environmental barriers, but in my PhD, I'm trying to tackle or at least have a look at all of them. Let's start by the environmental barriers. You might think that it's strange to say that there are environmental barriers when we speak about reuse, but the reality is more complex because reuse is not intrinsically more sustainable. Reality, as I said, is more complex because at the moment there is no clear definition of what are the benefits of the reuse strategy, so what really are the benefits given by this strategy. Then there's a lack of data, and without the data we cannot base a model or we cannot base our assumption on to do a good environmental assessment and to come with values that we can use to communicate to stakeholders so that we can use to then compare it with other circular strategies such as the recycling. And last, there is still some confusion of how to assess these circular strategies such as the reuse and the remanufacturing in the common methodologies that we use, such as the LCA or the Environmental Product Declarations, also known as EPD. Because this framework, when they were designed, these methodologies, when they were developed for linear products or for a linear economy. So there's some confusion in the literature, in the standards of how to include reuse and remanufacturing strategies into this framework. Nevertheless, all of these challenges that are highlighted here, or barriers, they don't exist alone. They influence each other. And I'm going to give you an example with the technical challenge. You listened or you learned in the previous presentation that the strength of aged glass might be lower compared to the new glass. And this leads to a lower yield of the glass panels that we can recover out of the double glazing unit or triple glazing units that we collect from the facade. And then lower yield means higher environmental impacts. Another example, the glass type. So in an IGU, we can have coated glass, laminated glass, and not only monolithic glass. And at the moment, according to the technical knowledge, we can only safely reuse monolithic uncoated glass. Therefore, when we collect and when we dismantle an IGU with a laminated glass or a coated glass, we will then have a lower yield. And this lower yield, again, is translated in higher environmental impacts. This is then to show you that the technical barriers, they don't only affect the feasibility of the reuse strategy of post-consumer glass, but they directly shape the environmental outcome of it. And that's also to say that if we want to aim at scaling up the reuse or the remanufacturing of post-consumer glass, we need to develop a systemic approach that tries to address all of these problems and not only trying to look at one of them. So, for this reason, I performed an environmental assessment of the reuse preparation process, which is following the IGU disassembling. And I'm going to explain you after what I mean by reuse preparation process. Briefly, the LCA methodology is a method when we assess the impacts of a product or a process, and this consists of different phases defined by the standard, which is the goal and scope definition, followed by the LCA inventory, where we collect the data about the impacts of the input and output that happen across the process that we are considering, and then we classify the impacts of this input and output into different indicators, which is not only the climate change that we are used to hear about at the moment, but there are many others, such as the eutrophication process, the land use, and so forth. So the goal of my assessment is to assess the emission of the reuse process and identify the hotspot of this process. So where we need to look at to decrease the environmental impacts. Therefore, this is a closed chain or a scheme of how it would look, a closed chain of reuse and recycling together, because as I said, not all the glass is good enough to be reused. Therefore, there is space also for recycling or downcycling for those paints which are not suitable for reuse. And then the process selective deconstruction, preparation for reuse, and sorting are included in my assessment. The most important process is, of course, the preparation for reuse. The preparation for reuse are the processes which follows the collection of the glazing from the facade. So it includes the transport to the disassembling facility, the IGU separation, which is followed by an edge trimming of the edge, which presents some sealants remaining, and the trimmed edges are considered to be sent for collected in a container and sent for recycling treatment. Then there's washing of the panel, followed by a quality inspection done with the scanner, and then according to the quality that has been assessed with the scanner, we can do a sorting of their quality. And then the glass that is good enough to be reused can be then ready to be reused and remanufactured, and those which are not good, the panel that are not good enough, can be again collected in a container and sent for recycling treatment. So the input of this process is the IGU, and the most important process and crucial process is the IGU separation. The IGU is a product which is not designed to be disassembled, but yet we can manage to disassemble it. Why is not designed to be disassembled? Because the connection between the materials, because IGU is a multi-material assembly, are mainly adhesive connection. As you can see in this connection diagram, there are far more adhesive connection, and those on which we need to work on, or that we need to break or open, are the connection between the link 4.1 and 3.1. And to do this, we can do it by hand, but as you can imagine, this is quite a work. And for this reason, EGLA, which is a machine manufacturer, developed a machine which is able to easily disassemble the panels and so breaking the links that I've shown you before. And if you follow the presentation of Henrik yesterday, you know the details about it. So once we separate the IGU, we can have the two panes with the remainings of sealant and as well the frame. So the panes can be collected and stored, and the frames can as well be collected in a container for further treatment. For the edge trimming, what are the edge trimming? As I said, there are some remainings of sealant on the edge of the IGU, and to completely get rid of it, the edge trimming consists basically in trimming the edges and recavating or having some stripes of glass which can then be sent for recycling. The assumption of my process is, of course, that we are considering a functional unit of 1 square meters of glass ready to be reused and remanufactured. The input is a double glazing unit with a symmetric configuration made of 4-16-4 configuration. The efficiency of the disassembling machine, I've assumed it's equal to 100%. The output of the process, set aside the glass for reuse and the glass waste for recycling, are the aluminum spacer and the sealants, which I've considered to be sent to landfill, so to be processed as waste in landfill. And then I've also done two comparative LCA study where I where I've done different transport scenarios and recovery rate scenarios to assess how these are impacting on the environmental outcomes. This is the life cycle inventory that I've used in my study, and I'm going to focus on the assumption. I've considered that the dimension of the glass is small enough to, in order for so the weight of the total IGU is below 50 kilograms, so it can be handled by hand. So there is no need to additional tools or machinery to do so. Then the transport is done by truck with a capacity of 32 tons. Then the waste, the glass waste collected at the edge trimming process is equal to 5 centimeters of glass collected from each edge. And then as well, the losses which came at the quality inspection step, so the glass that, according to the scanner, is not good enough to be reused, is sent again for recycling treatment, and then to therefore feed a closed-loop recycling of the flat glass. These are the results for the global warming potential of the process, grouped by different processes. And as you can see, the cullet treatment is the process which is impacting the most on the total CO2 emission. And the total CO2 emission for the whole reuse preparation process is equal to 0.33 kilograms of CO2 per square meters of glass. And to give you an idea, the emission of the float manufacturing process is equal around to 10 kilograms of CO2 per square meters of glass. So we are speaking about 30 times lower. These are the results for the total primary energy, including the both renewable and non-renewable primary energy, which is equal to 5.26. And as expected, the electricity used across the different processes is the one impacting the most. This is the comparative study that I've done, where I modified or I did different scenarios, changing the yield of the process, so the yield at the quality inspection done with the scanner. So I varied it between 33 and 63, and as you can see, by increasing the yield, we lower the environmental impacts. And here the transport distance is set to 100 kilometers. Another comparative study where I modified instead the transport distance, ranging from 100 kilometers to 500 kilometers, and again, by increasing the transport, we increase the emission of the process. To draft some conclusion, we've learned that there is potential for the reuse, as it has low embodied carbon. Transport and cullet treatment are the processes impacting the most. Then the losses during the process are the most important factor impacting on the environmental impacts. And then I want to conclude with these results, or all the assumption that I've done, is based on again, assumption, and we need to validate those with real operational data coming from the machine, coming from the projects, coming from real data. Next steps that I can identify is, of course, to extend the LCA assessment to other glass types, so an IGU including coated glass, laminated glass, and then again, investigating how the different losses that can happen during the transport process of the IGU or during the IGU disassembling, because one pane, one IGU can broken, and then, of course, we can have a lower yield. And then, to conclude, I would like to show you this picture where it's basically showing me doing a survey and testing the customer behavior when it comes to having defects on the glass, because that's how maybe we expect it would be with the reused glass. So feel free to reach out if you want to speak about this topic or others, and thank you for the attention.